Hello everyone, I'm honored to be here today to present our recent work towards explicit geometry-reflectance collaboration for generalized LiDAR segmentation in adverse weather. I'm Long Yang from University of Electronic Science and Technology of China, and this work is done together with my collaborators from Dalian University of Technology, Lancaster University, and Tongji University. I will discuss the 4 sections from Introduction, Methodology, Experiment, and Conclusion. LiDAR point cloud semantic segmentation is a fundamental task for 3D scene understanding, and it's crucial for applications like autonomous driving. However, most current methods are trained and evaluated on data collected under ideal conditions, like clear sunny days. Unfortunately, real-world environments are far more challenging. They involve factors like fog, rain, and snow, which current datasets often fail to capture. In adverse weather, the LiDAR point cloud suffers from severe disturbances, noise points, geometric perturbation, intensity distortions, and missing points. For example, in rainy and snowy days, there are many noise points in the red circle. In foggy days, there is a lot missing in the point cloud. This makes it really hard for models trained on clean data to generalize, causing a significant drop in performance. The intuitive solution is to collect more real-world severe weather data. But in reality, it's very difficult. Collecting diverse, high-quality adverse weather data and performing point-wise annotation on these data is time-consuming and expensive. Previous works tried using weather simulators with physical model to simulate severe weather data, but these physical models cannot fully reproduce real-world complexity. Other methods use data augmentation to improve robustness, such as PointDR uses point dropping, adds noise points, performs random jitter, to enhance diversity of training data. But these data augmentations may introduce redundant and futile information, making model training harder. For this problem, we take a different perspective. Let's look back at the LiDAR sensing principle. The LiDAR system emits laser beams, which are reflected back from surfaces, and the receiver collects the signals to record the 3D spatial coordinates, x, y, z, along with the reflectance intensity, r. In adverse weather, both spatial coordinates and reflectance intensity are affected. Besides shifts in spatial coordinates caused by things, like atmospheric refraction, the strength of the reflected signal can also change significantly. This is partly due to energy loss from effects like scattering in bad weather, and also because weather can change the properties of surfaces. For example, when it rains, surfaces get wet, and covered in water, which alters how they reflect signals. We conducted a statistical analysis, and found that the geometric layout, basically, how the points are distributed with distance, stays relatively stable between clean and adverse conditions. On the contrary, the reflectance intensity distribution changes a lot. There is a significant difference between the distribution of reflectance intensity under standard conditions and severe weather. This suggests that reflectance may play a key role in poor generalization. To verify this, we did an experiment. We simply removed reflectance information from input to train model. Surprisingly, the MIOU on the target domain semantic SDF dataset improved significantly, from 24.4 to 37.3. This suggests that the reflectance intensity does damage the robustness of the model. So, we can improve the model's performance in the target domain by removing the reflectance intensity. However, as shown in visualization examples, reflectance still contains valuable semantic clues, like the shapes of cars and roads can be recognizable even under snow, fog, and rain. Thus, directly discarding reflectance is suboptimal. In order to make full use of these two information, we propose our solution, GRCnet. In Geometry Reflectance Collaboration Network. First, we explicitly separate the feature extraction for geometry and reflectance, using 2 specialized encoders. Then, we design a robust multi-level feature collaboration module, to enhance the robustness and complementarity of the features. Finally, we fuse the features through both local and global strategies. For geometry encoding, We use a voxel-based encoder, which voxelizes the point cloud into 3D grids. This helps reduce sensitivity to noise and distortion in 3D space, and is well suited for encoding geometric features. For reflectance encoding, we select an image-based encoder. We first project the point cloud onto a 2D range view image by spherical projection. For computational efficiency, we use 2D depth-wise separable convolution block to build the 2D encoder. And we use instance normalization to mitigate distributional shifts in reflectance intensity. Although separating feature extraction helps to get purer features that are not interfering with each other, weather-induced noise and distortions still exist. To handle this, we design a robust multi-level feature collaboration module, which includes complementarity-aware information constraint, local-level fusion and global-level fusion. The goal of complementarity-aware information constraint is to encourage each encoder to extract discriminative and complementary features. Specifically, we first predict the mean and variance of each feature, then model its distribution. Then we use the CIC loss to constrain feature distribution. KL in the formula denotes Kullback-Leibler divergence, and R refers to the prior distribution of features. Here we use the standard Gaussian distribution. The first two items of CIC loss pull the feature distribution towards a standard Gaussian. This can reduce domain-specific noise and learn robust task-relevant features. The last two items of CIC loss keep the distribution of geometry features and reflectance features away from each other. This can encourage decreased correlation between these features, reduce redundancy and encourage complementarity. For feature fusion, locally, we fuse the features dynamically based on their uncertainty. More reliable features are weighted higher. Globally, the most direct way is to use the cross-attention between the two features, but this calculation is expensive and the GPU memory occupies high. We use a two-stage cross-attention mechanism with learnable tokens as bridge, to model interactions efficiently without heavy memory overhead and expensive calculations. Finally, we concatenate the locally and globally fused features, decode them using a 3D voxel decoder, and apply standard segmentation loss combined with CIC loss during training. We conduct main experiments under two domain generalization settings, semantic kitty to semantic SDF, and SIN LiDAR to semantic SDF. Semantic kitty is a commonly used normal weather dataset. SIN LiDAR is a synthetic point cloud dataset. Semantic SDF is a real-world adverse weather dataset, which has 250 scans for evaluation. Our method performs well under both two settings. Especially in semantic kitty to semantic SDF, compared to baseline, we have a huge improvement of 18.1 MIOU. Compared to the best previous method, RDA, we also have a significant improvement of 3.0 MIOU. In semantic kitty C, a simulated corruptions datasets, we also outperforms previous SOTA method. It also works well with different backbones like SPVCNN. Moreover, GRCnet consistently outperforms the baseline across different distances. Here are some qualitative results. Green points are correct predictions, while red points are errors. The MingNet with reflectance as input performs the worst. By excluding reflectance strength, there is a very large increase. Our approach further improves performance. You can see that our method produces much more robust and accurate predictions. In conclusion, we tackled the domain shift caused by changes in both geometry and reflectance. We proposed GRCnet to explicitly separate and collaboratively utilize geometry and reflectance features. We designed a robust multi-level collaboration module to suppress redundant information. Our results establish a new state-of-the-art performance under adverse weather conditions.